Hey everyone, I hope you all are doing good. So in this lecture, we're going to be starting with the Pascal's identity and we're going to cover three corollaries, right? So the idea is very simple. Pascal's identity is basically based on the binomial theorem that we covered in the previous lecture. So if you haven't covered the binomial theorem yet, I would highly suggest that you do. It's a pretty complicated concept. The last lecture in which we covered the binomial theorem, that is complicated. So I would really suggest that you cover it first and understand it and then move on to this one. So the goal of this lecture is very simple. We're going to understand Pascal's identity, the triangle, what this means, and also prove it. After that, we're going to prove three different corollaries, which are going to be very simple to understand. I'll do all this stuff using the animations that I make. Okay, so let's start with the binomial theorem first. Just a quick summary of what the binomial theorem is. So if you have anything x plus y to the power of n, right? Now, instead of us having to know every single formula, there's a general pattern to it. And this is the formula for it, or I should say the theorem. The idea is x plus y to the power of n is basically the sum from k0 to the value n, cn comma k multiplied by x to the power of n minus k multiplied by y comma k. So anything x plus y to the power of n can be represented with this over here, the sum of this term. Okay, let's just quickly understand what each of these terms represent. This is the coefficient, right? I hope you're able to understand why. We covered this, that this would be the coefficient. Now, once again, if you don't understand exactly why, how do we have this combination as the coefficient? I've covered it very clearly in the binomial theorem lecture. Okay, I think this is more easier to understand. You have x n comma k and y to the power of k, right? Let's just take a look at quick example. Let's say I have x plus y to the power of x plus y square, right? It's pretty much x square plus 2xy plus y square. Okay, so if you look at the coefficients, right, these are going to be the coefficients. The coefficients are going to be cn comma k. You can try to calculate it. It's pretty much going to be c in this case would be 2 comma 0. In this case, it would be c2 comma 1, and then this case would be c2 comma 2. Okay, and also if you look at the values of x, the powers of x and y, right? Take a look at this carefully. As you move on k from 0 to 1, 2, 3, 4, you keep on subtracting the value k from x to the power of n minus k, and you keep on multiplying it by y to the power of k. So every single time, whatever x started with, x starts with x to the power of n, and you keep on reducing one power from it. So you keep on reducing it, and you keep on multiplying and adding a power to y, right? So if you look at this example, you started with x squared, which is n, x to the power of n. Then you reduce the power of x by 1. That's why you have just x over here, and you multiply it by 1y. Then you reduced x completely, and you're left with y squared. So I hope that makes sense. Okay, so I hope you're able to understand this entire concept of the binomial theorem, right? Now let's understand the Pascal's triangle. So the idea is very simple. Think about this, right? Think about you solve x plus y n for values from 0 up till 6. So this is basically the value n, right? Now, if you solve it and you take out all the coefficients of whatever equations you get, this is going to be that triangle. Now, that's exactly what we're going to try to understand, right? Just to give you guys a quick example, think about the row 0. X plus y to the power of 0 would be 1, because anything to the power of 0 is 1. Okay, if you look at x plus y to the power of 1 would be x plus y. That's why the coefficients are just 1, 1. And if you look at the row 2, x plus y to the power of 2 is x squared plus 2xy plus y squared. And that's why you have these coefficients, right? Which is 1, 2, 1. Okay, so all we have done is very simple to understand. We have pretty much just written down all the equations for x plus y to the power of 0 to 6 and written down all their coefficients, right? Now, there's a very important property to understand from this, and that is what the Pascal's identity is. Okay, so just a quick understanding once again, the row n is the coefficients of x plus y to the n, which is this formula. Now, let's understand how exactly can you build it, right? Now, one way is obviously that you can just write down the formulas, right? And you can build it, take out their coefficients, use this formula to find the coefficients. There's another way to this as well. So the idea is both edges are always 1. what you need to do is start with making a triangle, and every single time just keep on adding ones to the edges. So this side over here are our edges. If you look at this triangle, right, all the edges are pretty much 1, right? So in the first case, you have just 1, then 1, 1. Then you have 3 values where the last 2 are 1, right? And same thing goes for, keeps going on. So if I wanted to extend it, if I wanted to extend this triangle for row 7, then I would add 1 at this end and another 1 at this end, right? Just pretty much it keeps on increasing that triangle. Okay, so that's the first idea on how to build it. And this is second point is, every interior entry is equal to the sum of the 2 entries directly above it. Now, this is the important part to understand. Okay, I want you guys to take a look at this triangle carefully, right? Look at the pattern that's happening. If I add 1 plus 1, if I add 1 plus 1, this value, it gives me 2. If you add this 1 and this 2 over here, this would give you 3. If you add this 2 and this 1, once again, you would have 3. Okay, let's add this 1 and this 3, it would give you 4. Same thing you can do if you do 3 plus 3, it would give you 6. The idea is that whatever the values you have, every interior entry is the sum of the 2 entries directly above it. So it's pretty much that whatever 2 values you have, whatever comes in the middle below it is pretty much going to be the sum of it. So think about if I wanted to extend this triangle now for row 7, right? What I would do is I would sum these values up. So I already added 2 ones at the edges, right? So one part is done, the first step is done. Second step is every interior entry equals the sum of the 2 entries above it. Okay, so this entry, which is going to go directly below in the middle of the 1 and 6, would be 7. Okay, this entry would be the sum of 6 plus 15, which is going to be 21. This entry would be the sum of 15 and 20, which is going to be 35. Okay, once again, you have 35, then you have 21, then you have 7, and then you have 1 at the end. So I didn't have to do the Cn kind of equation. I didn't have to write this entire equation. In order for me to find the coefficients, I just drew the triangle, drew the coefficients, 1 at the very end of the edges. And second point is, I can just sum the 2 entries directly above something, right? So I hope you're able to understand. And this example, or I should say this property, is what we call the Pascal's identity, right? This is exactly what we are covering in this lecture. Okay, so I hope you're able to understand the idea of what's happening. Now, let's take a look at the actual identity, and then we will do a proof of it. Okay guys, so I've given the Pascal's identity on the board. Let's just try to pause the video and take a look at this identity over here. Okay, so the idea is very simple once again. This is only just saying that Cn plus 1 or anything, any value that you have, any coefficient, is pretty much the sum of the 2 coefficients above it, directly above it. Right? That's exactly what this term means. So let's just take a look at, let's just try to understand this once again, right? So our row is pretty much represented by the value n, right? N is the row. So if you do n plus 1, that would be another row, or next row I should say. So it's saying n plus 1 comma k is the previous row. So n would be the previous row, comma k minus 1 plus cn comma k. This k minus 1 and cn comma k is pretty much the 2 coefficients that are directly above it. Very simple to understand, right? Okay, so let's just quickly take a look at one of the examples. Let's take a look at, consider 4 and 6, and let's try to prove that this gives you the value 10, right? Okay, so let's take a look at the value of n over here first. In this case, the value of n would be 4, right? Because we are in row 4. So C 4 comma, what's the index of this? What's going to be the value of k? You start k with the value 0. So in this one, this is 0, this is 0, 1, this is 0, 1, and 2. So for this one, this index is 0, this is 1, this is 2, this is 3, and this is 4, right? So just wanted to quickly confirm that n is going to start with 0 and k is also going to start with 0, right? Okay, so I have k value 1 and n value 4. So it's going to be C4 comma 1 plus C6 comma, sorry, I should say C4 comma 2. If you add it together, you get C4 5 comma, this case is going to be 0 1 2 2. Now take a look at this, right? C4 comma 1 is the value 4, C4 comma 2 is the value 6, and this results in the value 10, which is C5 comma 2. You can confirm this, row 5, which is N5, and index 2 or K value 2, which is 0 1 comma 2. Right, so I hope you're able to understand the Pascal's identity. Very easy to understand. It's just that you need to have a good understanding of the binomial theorem first. So I would highly suggest that if you haven't watched it, take a quick look at the video once again. Okay, so now let's try to understand how do we actually come to this Pascal's identity, right? We need to actually show a proof of this identity. So I'm going to show the proof using an animation. So according to Pascal's identity, Cn plus 1 comma k equals Cn k minus 1 plus Cn comma k, right? What we're going to do is we're going to prove it by counting the same set in two different ways, right? And we're going to use the example of bit strings of length n plus 1 with exactly k ones. Okay, so let's take bit string of length n plus 1 with exactly k ones, right? So for an example, we can use n equal 3 and k equal 2. That means the length is 4 and we have two ones. This gives you C42 equal 6 bit strings in total, right? And here are all the bit strings that we have. Okay, now partition these bit strings by their first bit. So what's gonna happen is every bit string starts with either 1 or 0. So if you look at these carefully, right, the first three start with 1 and the last three start with 0. So first bit is either 1 or 0 and it is never both. So if you separate it on the left hand side, you see we have all the ones that have the first bit equal 1, and on the right hand side we have the first bit equal 0. So 3 bit strings for the first bit 1 and 3 bits for the first bit 0. Nothing is missed and nothing is double counted. Okay, now count each group using n and k. So group 1, it starts with a 1, right? That first one uses one of our k required ones. So the remaining n position need k minus 1 more ones. So the count of length n bit strings with k minus 1 ones would be Cn, comma k minus 1. So for an example, with n equal 3, that would be C3, comma 1, which is equal to 3. And it matches the number of bit strings that starts with 1. Now let's take a look at the group 2. Okay, so group 2, it starts with a 0, right? That means the first bit uses 0 once, right? Remaining n position need all k ones. So the count is Cn, comma k. Okay, so remaining n positions need all k ones and count as Cn k, right? So for our example, this would be C3, comma 2, which is equal to 3. And again, it matches, right? 3 bit strings start with 0. Okay, now the final part. Now, what you do is you sum the two groups together. So group 1 plus group 2 would be the total, which is Cn, comma k minus 1 plus Cn, comma k equal Cn plus 1, comma k. Now, this is exactly the Pascal's identity. Now, if you notice, our argument only used n and k as the parameters, right? At no point did we rely on n being 3 or k being 2. This same reasoning works for any value of nk. And that's what makes it a proof and not just an example. Okay, everyone. Now let's understand the three corollaries that we have, right? Okay, so let's first understand what does this word even mean. The idea is very simple. A theorem is pretty much a major proven result, right? Whenever you have a theorem, it's pretty much that you've spent a lot of time and it's a big result, right? It's a big achievement. Corollary is something that is followed from the theorem, right? Basically, you have a theorem now, and you try to find out things and other results using that theorem, and that's exactly what you call a corollary, right? Okay, so the binomial theorem holds for any x and y. So what we're going to do is we're going to pick clever values of x and y, and we will get identities from it, right? Which will be the corollaries that we look at. So once again, the idea is very simple. You already know the binomial theorem, which is a major result. What we're going to do is we're just going to pick up some specific x and y values, and that will give us some identities, right? Which are very important. So I'm going to quickly explain all three of them on the board first, and then I'll show you the animation proofs of these corollaries as well. Okay, so I've given the binomial theorem over here just for reference. Okay, this is the binomial theorem you have. So first, let's take a look at all the three corollaries and what we are doing. In the corollary 1, we are setting the x and y value to be 1, 1. In second one, we are setting x to 1 and y to minus 1. And in the third one, we are setting x to 1 and y to 2, right? Okay. Now let's try to understand the corollary 1 first. So if you set x and y to 1, think about this, right? If I set x and y to 1, that means I can write it as 1 plus 1 comma n. You understand this part, right? I hope this makes sense. So if x plus y is 1, you can write this as 1 plus 1 comma to the power of n. So 1 plus 1 to the power of n. And if you write the right hand side now, it's pretty much cn0 plus cn1 all the way up to cn comma n. Let me just try to quickly explain why. Okay, think about this, right? If x and y are just 1, anything to the power of 1 to the power of n minus k or 1 to the power of k. Y and x values are fixed, right? They're always 1. So if you do anything to the power of 1, it's always going to remain 1. So we can just remove these terms out of the equation, right? So if x and y are 1, this x to the power of n minus k and y to the power of k doesn't really matter. It just gets removed from the equation. So you're left with the sum of the coefficients, right? And what is the sum? It's pretty much n0 to n1 plus all the way up to cn. Okay, so what is 1 plus 1 to the power of n? It is 2 to the power of n. So 2 to the power of n, if you do this, is pretty much the sum of the coefficients, and that's what the first corollary proves. So the idea is sum of any row of the Pascal's triangle is 2 to the power of n. Very simple to understand. Once again, the idea is simple. I picked up the values x and y equal 1. Okay, so if I do 1 plus 1 to the power of n, according to the binomial theorem, that should be equal to the sum of this. Now, since x is 1 and y is 1, x 1 to the power of anything, it doesn't really matter. So I can just get rid of both of these terms in this corollary, right? Okay, so what I'm left with is only cn comma k, the sum of cn comma k, which is pretty much cn comma 0 plus cn1 all the way up to cn comma n. So what this means is 1 plus 1 to the power of n, which is 2 to the power of n, is the sum of Pascal's triangle, is the sum of the row of Pascal's triangle. That's what the first corollary proves. Okay, so I hope you're able to understand. Next one and the third one are also once again very similar. In the second one, we are setting x to 1 and y equal minus 1. Okay, so this pretty much means that on the left hand side, x plus y to the power of n, you can write it as 1 minus 1 to the power of n, right? What would be the right hand side? Once again, think about this, right? X is 1, so x to the 1 to the power of anything wouldn't really matter. I can get rid of it. That's why you don't see any x to the power of something over here. And we also don't have any y in this equation, right? Why? Because y is also minus 1. Okay, but since y is minus 1, there's an important thing that's happening in this equation, right? If you look at this, right, it started with cn comma 0, then it changed to the sign negative, then it changed to the sign plus, then it changed to the sign negative again. Why is this happening? Think about this, right? If you have minus 1 to the power of anything odd, that would be minus 1. If you have minus 1 to the power of something even, that is going to be 1. Think about this, right? So cn comma 0, right? Minus 1 to the power of 0 is 0 to the power of, I should say, any number to the power of 0 is 1. Okay. Cn comma 1, if you take a look at minus 1 to the power of 1, that would be minus 1. So all the odd powers, all the values where Cn, comma, odd number is there, you have a minus sign next to it. And if you sum it all together, right, if you do the entire sum, it would result in 0. That's the entire point of the corollary too. So the idea is that the alternating row sum is pretty much equal to the value 0. Once again, just a quick summary. In the corollary 2, we are setting x to 1 and y to minus 1. So if you do 1 minus 1 to the power of n, on the left hand side, that will be equal to the sum of all the coefficients. Why? Because we don't have the x and y, since x is 1 and y is minus 1. But since y is minus 1, wherever the value of k is an odd number, it is alternating. It's changing to a negative sign. And if you sum it all up, it results in a 0. Let's just take a look at a quick example, right? Consider x square plus 2xy plus y square. So this is index 0, 1, 2 according to the k values, and the n value in this case would be 2, right? Okay, so let's just quickly add this up, right? That means you do c 2, 0 minus c 2, 1 plus c 2, 2. If you add this up, you get 1 plus, or I should say 1 minus 2 plus 1, which is equal to 0. That's exactly what this identity is saying, right? I'll also try to give an example of this one. The idea is very simple once again. So if I have, let's consider row 4 for now. So 4 is 1 plus 4 plus 6 plus 4 plus 1. These are the coefficients when n equal 4, right? If you guys don't understand this, try to pause the video. You can take a look back at the Pascal's triangle at row 4. So if you add these all up together, right, this is 5. This would be 1 plus 4, which is 5, plus 5, 10. This is going to be 16, and 16 is equal to 2 to the power of 4. So if you want to confirm, you can pause the video and try to confirm these corollaries by taking a step back. And I would highly suggest that you do, to just get a nice understanding of all three of them. Okay, so I hope you're able to understand the first two. Now let's take a look at the third one. Once again, in the third one, all you're doing is you're setting the value of x to 1 and y to 2. So let's write the left hand side first. You can write the left hand side as 1 plus 2 to the power of n. You can write the right hand side equal to the sum of 2k multiplied by cn comma k. Let's just quickly understand this. Okay, once again, since x is 1, anything to the power of 1 would be 1 again. So we can just entirely get rid of x in this equation. Secondly, you have y is equal to 2. So you're only left with this term and the cn comma k term. So since y is 2, you write it as 2 comma k, and you're only left with this term and this term, right? And that's why 1 plus 2 to the power of n is equal to sum of 2k. This 2 is what yk represents, multiplied by cn comma k, which is equal to 3n. So what this means is, if you multiply a coefficient by 2 to the power of k and sum, you get 3 to the power of n. So the idea is very simple. If you multiply the coefficients by 2 to the power of k and you sum them up, you get 3 to the power of n. Let's just take a look at this example once again. I'm going to consider this example, right? Okay, so I have 1, 2, 1, right? The coefficients of x squared plus 2xy plus y squared. Okay, so in order for me to get 3n, I multiply it by 2 to the power of k. So I multiply it 1 by 2 to the power of 0, this by 2 to the power of 1, and this by 2 to the power of 2. So I get 1 plus 2 plus 4. 1 plus to the power, this should be 1 multiplied by 2 and 2, 1. So you have 2, 0. You have 2, 1. And you have 2, 2. This gives you 1 plus 4 plus 4. My bad. So this will be 1 plus 4, resulting in the value 9, and hence your answer, which is equal to 3 to the power of 2, right? Or I should say 3 to the power of n. So the corollaries are very simple to understand. Once again, it's just that the entire point of all three of them is you have the binomial theorem. You're setting the values x and y to be 1, 1, 1 minus 1, and 1, 2. And you get a theorem, or I should say, sorry, you get some resulting identity as a result of doing this, right? Okay. Now let me just quickly show you guys one of the animation to explain all three of them once again. Okay. The binomial theorem holds for any x and y, right? So if we plug in specific values, we get the identities for free. Let's try it now. Okay. So start with x equals 1 and y equals 1. So left side becomes 1 plus 1 to the power of n, right? And that's basically 2 to the power of n. Now on the right hand side, every x and y raised to anything becomes 1. The coefficients cn comma k remain. So the sum of all the coefficients equals 2 to the power of n. Now you can verify this with the row 4 of Pascal's triangle. So if you just compare the row 4 and take a look at it, what you get is 1 plus 4 plus 6 plus 4 plus 1, which is equal to 16, and which is 2 to the power of 4, just like we saw in the lecture, right? And it works. Okay, now let's try to take a look at corollary 3. Sorry, 2. So now set x equals 1 and y equals negative 1. So left side is 1 minus 1 to the power of n, which becomes 0 to the power of n, which is basically the value 0. Now on the right hand side, the x terms are still 1, but the y terms take the alternatives, right? Because of k. So positives, so it's basically positive when k is even and negative when k is odd. This gives you result cn comma 0 minus cn minus cn comma 1 plus cn comma 2 minus cn comma 3 and so on. And this total equals 0. So let's just check this for row 4 now. 1 minus 4 plus 6 minus 4 plus 1 equals 0. And that's done, right? And if you look at this, the even sized subsets are equal to the odd sized subsets. Very important to understand. Okay, last one. Set x equals 1 and y equals 2. So the left side is basically 1 plus 2 to the power of n, which is basically 3 to the power of n, right? Now on the right hand side, x terms are still 1 and y to the k becomes 2 to the power of k, right? So the coefficients stay. So the sum of 2 to the k times cn comma k equals 3n. You can check this again with n equals 2. So let's just quickly check it. The row 2 basically becomes 1 times 1 plus 2 times 2 plus 4 times 1, which is 9 equal 3 to the power of 2. Okay, so I hope you're able to understand these three corollaries. Three identities from one theorem, and clever plugin basically gives in a new identity, right? And that's the plugin trick that we just used. Okay, everyone. I've given these two questions on the board, so try to pause the video and answer them. Okay, for the first question, very simple to understand. Use Pascal's identity to find C8, 3 given C7, 2 and 7, 3 equal 35. This is simply the Pascal's identity. So C8, 3 would simply be 21 plus 35, which is going to be 56, right? I hope you're able to understand. We simply use the Pascal's identity. Okay, now let's take a look at the second one. This is a bit tricky, I should say. So the idea is, what is C20, 0 plus C20, 1 plus C20, 2 all the way up to C20, 20. Okay, now this requires the use of corollary 1 that we covered. If you remember, we covered 2n 2 to the power of n equal sum of all coefficients of row n. And if you look at this equation, right, this is pretty much the sum of all the coefficients of row 20. So I can say that this would pretty much be, the answer would be 2 to the power of 20 for this question. Okay, so I hope you're able to understand this lecture. Once again, if there are any issues or any problems that you guys are facing, let me know in the comments. I'm very active on my YouTube channel. I can just quickly respond. And I'll also give my Discord ID in the description or maybe in the comment section. So if anybody has any questions, you can just message me on Discord. Right, so I hope you're able to understand all these questions. Once again, any feedback for me, let me know. And if you guys are able to understand the animations, let me know if there's any changes or any improvements I can make to them as well. Okay, I'll see you guys in the next lecture.